Hey everybody, we've had a special request to work this problem, so let me go through it with you. A roller coaster car with a ball hanging down by a string. It sits at rest and then it accelerates at point B and then it moves up this incline at a constant velocity. Acceleration is 0 here, and then it accelerates down the incline and then it goes through this loop accelerating towards the center. We have a centripetal acceleration there, and this is a radius of 25 meters through this loop. It says when we're at point A right here, draw the free body diagram of it. Well, that's really straightforward. There's going to be a gravity force down and a tension force up in that string, and they must be equal. The mass of the ball is 1 kilogram. Just to make life simple and the math simpler, I'm going to have G equal 10 meters per second squared. So I get a gravity force here of 1 Newton. Therefore, the tension right here must be 1 Newton as well. And now in the next parts, it says what happens in part B when we're right here. We're accelerating to the right. And it asks us to do two things: find the horizontal and vertical, or tension in the X and tension in the Y in the string, and draw where the ball's going to be at this spot. Well, it's accelerating to the right, so the ball has to be pulled forward, so the ball has to be back here somewhere. That's going to give us a free body diagram that looks like this, with tension and a gravity force down, which we know is 1 Newton already. Now, it's accelerating to the right, not up and down. So that means that the horizontal portion of the tension is what is accelerating it forward, and the vertical part just must equal 1 Newton. So we already have this part. That's 1 Newton right there. So the horizontal part, Tx equals ma. Well, we know the mass is 0.1, and we know the acceleration is 5 meters per second squared, so we get 0.5 newtons as our tension here at this point. All right, our next part is where we are going up the incline, but it says we're going up at this velocity and not accelerating, constant speed. So the acceleration is 0, so there's no acceleration. So the forces must cancel out. That means the ball must be hanging straight down, and we should have a tension force up and a gravity force down that must cancel. So the horizontal part of that is 0, and the vertical part is our 1 Newton again. Right here, we're accelerating down the incline. So that ball has to be being pulled down the incline, because by itself it'll just want to fall, right? So it's going to be back here again somewhere. Now, we would normally draw a coordinate system like this, parallel and perpendicular to the velocity, to the acceleration. But they specifically want a horizontal and a vertical, ty and tx. So that's messing us up a little bit. So what they want is a coordinate system like this. So here's my free body diagram. I have a tension out this way. I have a gravity force down, which we know is 1 Newton already. We have to break this into x and y components. X, y. So here's my tx and here's my ty. And I'm going to have a component of the acceleration both in the x and the y direction. And that's 30 degrees here. Now, if you do that math, you get that this is a 30, 60, 90 triangle. So this is 2.5 meters per second squared on the y side. Now on the x side, that will be, what did I get? 4.3 meters per second squared. That's just geometry. Okay, that's the x and y components. So in the x direction, we have only one force, Tx, equals the mass times the acceleration in the x direction. The mass is 0.1 kilograms. The acceleration is 4.3 meters per second. So we get a net x force of 0.43 newtons. So 0.43 newtons. Let me check that. That's correct. Now, in the y direction, Ty equals ma in the y direction. Now, I have 2. Now, just to make life simple, I'm going to call down positive because it's accelerating down. So I get Ty negative, and I get a 1 Newton up. Sorry, not up, in the positive direction. So 1 Newton in the positive direction, Ty, which is upward, which is the negative direction, equals m, which is 0.1 kilogram, times our acceleration of 2.5 meters per second squared. That gives us 0.25 here. That gives us 1 Newton here minus Ty. So Ty equals 0.75 newtons. So 0.75 is our answer here. Okay, that was way harder than it needed to be because they just put x and y as our coordinate system. We would never do that. We would always put our parallel and perpendicular to make life simple so we didn't have to split up the acceleration. We've never done that in class. All right, and then this one, it says that we are going around the loop at this point. We're upside down. We have no tangential acceleration, no horizontal acceleration. So we only have an acceleration down. So that means that there can't be any side-to-side force. So we have 2 options. The ball either hangs straight down or the ball is up here. In order to figure that out, let's take a look at what our centripetal acceleration is going to be. Remember, it's v squared over r. And our velocity is 25 meters per second, that's squared, over the radius, and the radius of our loop was 25. So divided by 25, so the math is easy, it's 25 meters per second squared. I want you to notice 25 meters per second squared, which is our centripetal acceleration, is greater than g. That means it's accelerating downward faster than the acceleration due to gravity. That means it requires an extra force. That means the ball has to be up here being pulled down by the tension. So our free body diagram would look like this. We've got a tension and we've got the gravity force. So hey, that means that our Tx is still 0 because it's not accelerating right or left. And our Ty, or our vertical, is going to be these two adding up to give us an acceleration over here like this. So let me work it right here. The forces in the centripetal direction equals MAC. That's 0.1 kilograms times 25 meters per second squared, which we just calculated right here. And then our forces are, I've got tension plus mg, but we know mg is 1. And this will be 2.5. Oh, yeah, 2.5. Is that right? Yeah, that's correct. I just had a brain fart for a second. And then our tension is here. So tension will equal 1.5 newtons downward. Okay, so 1.5 newtons downward is necessary. And that, my friends, is the problem.